In this video, I'm going to cover the concept of limits at infinity. Now, there's a couple of things that we need to know first, and that is how to find a horizontal asymptote. If I have some rational function, and the rational function is defined by a polynomial divided by another polynomial, and polynomials are written so that they're written in descending orders of exponents. So I would expect that my second term in my numerator is going to be some coefficient times x to the power of n minus 1. And then my third term would be some coefficient times x to the power of n minus 2. I would expect the same thing in the denominator where I have descending order of exponents. My second term is going to be, I'll have an exponent of n minus 1 if it exists, and so forth, descending order of exponents. But when it comes to finding a horizontal asymptote, all of these other terms don't matter. It's really just the first term. So if the degree of my polynomial in the numerator is less than the degree in the numerator in the denominator, and when I talk about degree, I'm talking about the highest order exponent. So the highest order exponent, my degree, if the degree in my numerator is less than the denominator, then my horizontal asymptote is always going to be y equals 0. If my degree in the numerator is equal to the degree in the denominator, then my horizontal asymptote will just be the ratio of the coefficients of my leading terms. And then if my degree in my numerator is greater than the degree in the denominator, then I will not have a horizontal asymptote at all. So I'm going to go ahead and look at this first one here. I'm going to go ahead and graph this function right here. And this is a real basic, f of x equals 1 over x is a real basic rational function. But I'm still going to draw it and show how you can find it even if you don't recognize it. Now, the degree in my numerator is x to the power of 0, because that would give me 1. And the degree in my denominator is x to the power of 1. So I see that the degree in my numerator is less than the degree in the denominator, which means then my horizontal asymptote is going to be y equals 0. My vertical asymptote, the vertical asymptote is much easier to find because the vertical asymptote is the value of x that is not allowed. And the value of x that's not allowed is when x is 0, because 1 over 0 is undefined. So I have a vertical asymptote right here. Now my graph is either going to look like here and here, or it's going to be here and here. So I'm just going to pick some value on the right-hand side of my vertical asymptote. How about, I don't know, 1. And if I plug in x as 1 here, then I get a y of 1 over 1, which is 1. So my graph is going to look like this on this side. And then on the other side, either I have a graph here or here. So I'm going to find some x value that falls on the left-hand side of my y-axis. So say negative 1. And 1 over negative 1 is going to give me negative 1, which would mean negative 1 and negative 1. So I have a point down here in the third quadrant. So the other part of this graph is going to look something like this. And I'm going to do the same thing for all of these. I'm going to graph these, and then I'll go back and answer these questions. So I have a vertical asymptote at negative 3, because negative 3 plus 3 is going to give me 0. So at negative 3, 1, 2, 3, I have this vertical asymptote. Now I'm going to find some value on, so I either have a graph here or here. So I see that my terms, I have 3 times x over x as my leading terms. And since my degree is the same in the numerator and denominator, then I just go with the coefficients. So my horizontal asymptote in this case is going to be 3. So it's going to be 3 over 1, or just 3. So 1, 2, 3. So here is my horizontal asymptote. Now I'm going to find some value. Either my graph is here or here, so I'm going to find some value to the right. Something easy about, let's do 2, maybe 2. If I plug in 2, if x equals 2, then I have 3 times 2, which is 6. 6 minus 2 is 4. And then 2 plus 3 is 5. So if x is 2, so 1, 2 over here, then my y value is not even 1. It's less than 1. So we're looking at a graph that's going to be something like this here. Well, we're going to do the same thing on this side. So -1, -2, -3, -4, -5. Let's do -5. So I'm going to plug in -5. So when x equals -5, I get 3 times -5, which is -15. And -15 minus 2 gives me -17. So -17. And then -5 plus 3 is going to give me, -5 plus 3 is going to give me -2. And so that's going to give me a positive number, and that positive number is going to be at almost 9. It's going to almost be 9. So that's going to be way up. So when x is 1, 2, 3, 4, 5 over here, then my y value is going to be way up here. So we're looking at a graph like this. My next one. So I have well, what's going to make the denominator 0? So I have 3x plus 2 equals 0. I'm going to subtract 2 from both sides. That gives me 3x equals -2. Divide by 3, and that gives me that x equals -2/3. So we're getting a vertical asymptote at not even quite -1, so somewhere like this. If I look at my leading terms are going to be -2x over 3x. It looks like the degrees in the numerator and denominator are the same, so I'm just going to go with the coefficient. So that's going to be -2/3, so that's going to be right here, not even -1. So that gives me that my vertical, I'm gonna define these. I'm gonna define these. That my horizontal asymptote is going to be -2/3, and my vertical asymptote is, I should say it's horizontal asymptote is y equals -2/3, and my vertical asymptote is x equals, what did I figure out? It's -2/3, so it's the same. Now I'm going to find some value on the right side of my vertical asymptote. So how about 1, 2, 3? How about 3? We're going to plug in 3. So when x equals 3, then I have 1 minus 2 times 3, which is -6. So -6 plus the 1 gives me -5. And then that 3 times 3 is 9. 9 plus 2, 10, 11. It gives me 11. So we're looking at a really, really small number when we're way out here. It's also going to be negative, but the question is, I better find something closer over here. I think that would be more helpful. Let's do 0. 0 is super easy. So I'm going to plug in 0 here. That's going to give me, if x equals 0, then I have my y is going to be, this is gone and this is gone. It's going to give me 1/2. So 1/2. When x is 0, is going to give me 1/2, which is going to be here. So we're looking at our graph here. And then we'll do the same thing over here. We'll find something super close, so it's easier to find. How about -2? -2. So we'll plug in -2 when x is -2. Then -2 times -2 gives me a 4. 4 plus 1 is 5, my y value. And then -2, 3 times -2 is -6. -6 plus 2 is going to give me -4. -4, which looks like that this is going to be -1 and something. So -1 and something is going to be less than this -2/3. So I have a graph that's going to be down here. The next one, I'm going to find my vertical asymptote. Vertical asymptote is what will make this graph 0 in the denominator. That's going to be 1, a positive 1. So this is my vertical asymptote. Vertical asymptote is when x equals 1. And I can see that my leading terms are this x and x over -x, which would give me -1. So my horizontal asymptote is when y equals -1. So that would be here. So I'll find some value on the right hand side. Let's try 2. So x is 2, then y is, that would be 2 over and then 1 minus 2 gives me negative 1, so negative 1. That would just give me negative 2. So 2 over 1, 2, and then negative 2 would be down here. So my graph is going to be something like this. So the whole point of the graphs for rational functions is we converge. We have to converge on our asymptotes. In fact, that's what asymptotes are things that the graph converges on. And then we'll do the same thing over here. I'm going to try 0. 0 is going to be easy. So I have 0 over 1 minus 0, which is 1. So I have 0 over 1, so I get this point here. So if I plug in 0, I get another 0 back. So I would have another piece of my graph on this side. Let's look at the next one. Now I can see that no matter what I plug in for x, I will never get a negative in the denominator. So there is, so my vertical asymptote is none. My horizontal asymptote is going to be, well, I can see that my leading terms are the same, so I just look at the degree in the numerator and denominator are the same, so I just look at the coefficient, so that's 1 over 1, which is 1. So I get this graph like this. Now this is going to be a little bit harder because I don't know what this graph looks like. I mean, there is no vertical asymptote, but I'm going to converge on this line. So let's just throw in some values. How about when x is, how about negative 1, 0, 1? And we'll go from there and see if that helps. So if I plug in negative 1, then negative 1 squared is 1. 1 minus 1 is 0. So that's going to give me 0 over 2. If I plug in 0, then I get 0, 0 and 0 for my x squared. So that's going to give me negative 1 over 1, which is negative 1. And if I plug in 1, then I get 1 squared, which is 1 plus, let's do the numerator first. So I have 1 squared, which is 1, minus 1, which is going to give me a 0, and 0 over 2 is going to give me a 0. So that means that I have, at negative 1, I'm at this point here. At 0, I have 0, negative 1, it's another point, which is going to be here. And I have 1, 1, 0 over here. So it looks to me like the graph is going to look something like this. Now, if I couldn't find anything where I started, I think it's always helpful if you don't know anywhere to start, at least plug in 0. But I could try something else. I could have plugged in some other numbers and saw, I could continue out and try some other numbers. But in this case, I think I'm going to just get numbers that will be closer and closer to, as I put in larger x values or really small x values, I'm going to converge on this y equals 1. All right, so let's look at the next one. My horizontal, let's do horizontal asymptote. My horizontal asymptote is going to be, it looks like the degree in my numerator is smaller than the degree in the denominator, so the horizontal asymptote is going to be 0. And then my vertical asymptote, well, again, there's nothing I can plug into here that will give me 0 in the denominator, so my vertical asymptote does not exist. None. All right, so we're going to do the same thing. We're going to just throw in some values. We are going to converge on this line here. And so we're going to just do the same thing. We have negative 1, 0, 1. And then let's plug in these values. Negative 1. Negative 1 squared is 1. 1 plus 1 is 2. So I have negative 1 over 2. So I have negative 1 half. So that's 1 over and half down. And then we're going to do 0. If I plug in 0, 0 over 0 squared plus 1 gives me 1. So 0 over 1, which is just 0. And then I have 1. I'm going to plug in 1. I have 1 in the numerator. And 1 squared, which is 1, plus 1 gives me 2. So I get 1 half. But I'm going to, so it looks like I'm crossing over the asymptote, which is fine if it's a horizontal asymptote. You will never cross a vertical asymptote. So I crossed over the horizontal asymptote, but I still need to converge on this asymptote. So I'm going to converge on the asymptote from this direction, and I'm going to converge on the asymptote from the other direction. Another way for graphing that is helpful is to try to find your x, y intercepts. And that would have given me some other guidance if you choose to do that. So let's look at what the question is. It says here, for each of the following functions, I want to discuss the behavior near the asymptotes and hence deduce their equation. Well, I've already deduced their equation, at least for most of these. I think I still have to find I need to explicitly write down what my horizontal asymptote is. It's y equals 0, and my vertical asymptote in this case was x equals 0. In this case, I had a horizontal asymptote at y equals 3, and I had a vertical asymptote at x equals negative 3. So I think I have all of my vertical and horizontal asymptotes defined now. So then it says here, state the value of our limits as I approach infinity and negative infinity. So negative infinity, infinity. So my limit as x approaches negative infinity of my function, so as x approaches negative infinity, then my function of f of x is going to approach, it looks like it's going to approach 0. That approaches 0. And when x approaches infinity, then my f of x is going to approach, when x becomes super large, my graph, my y value approaches 0. We can also look what happens when we approach our other asymptote, our vertical asymptote. So let's look at when x approaches 0 from, let's look at when we approach from the right-hand side versus when we approach from the left-hand side. Oh, I should say it doesn't equal, these approach. So when I approach from the right-hand side, then I approach x equals 0, then my y just shoots to infinity. So this is going to be infinity. I approach f of x equals infinity. And from the other end, when I approach 0, then my y value approaches negative infinity. Let's do the same thing for this one over here. I want to examine when x approaches negative infinity, when x approaches infinity, when x approaches my vertical asymptote, in this case, which was negative 3, from one side, from the right side, and from when x approaches negative 3 from the left side. So, in these cases, I'm going to get, when x becomes super small, then my y, it looks like, approaches this horizontal asymptote at, what do we say the horizontal asymptote was? It was 3. When x becomes super large, my y value converges on that horizontal asymptote, so that also becomes 3. When I approach from the right-hand side, when I approach the negative 3, then my graph looks like the y value goes down to negative infinity. And when I approach negative 3 from the left side, my graph explodes to the upside to positive infinity. All right, the next one, same thing. I'm going to look at my graph as I approach my asymptotes. So from when x approaches negative infinity, when x approaches infinity, when x approaches my vertical asymptote was negative 2/3. So when I approach negative 2/3 from the right-hand side, or when I approach negative 2/3 from the left-hand side, and what does my function do? What does my y value, what does that do? So when x approaches negative infinity, my graph approaches this horizontal asymptote of negative 2/3. When x approaches some massively large number, my graph approaches that horizontal asymptote again, so that would be negative 2/3. When I approach from the right-hand side, when I approach x equals negative 2/3, my y value, when I approach negative 2/3 from the right-hand side, I explode to the upside, so infinity. And then when x approaches negative 2/3 from the left-hand side, I see that my graph goes down to negative infinity. Right? So when x approaches infinity, let's do when x approaches negative infinity, when x approaches infinity, when x approaches my horizontal asymptote at, vertical asymptote at 1 from the right-hand side, or when I approach 1 from the left-hand side. What does my function do? What are my x values? So when x becomes very, very small, my graph converges on that horizontal asymptote, which is -1. When x becomes massively large, the y converges on that the horizontal asymptote. So that's going to give me -1 as well. When x approaches 1 from the right-hand side, then the graph goes down. So that would be negative infinity. And when we approach 1 from the left-hand side, then the graph goes up. So that's going to be infinity. The next one, we're going to look at when x approaches negative infinity, when x approaches infinity, when x approaches, I don't really have a vertical asymptote, so I'm basically done after this. So after just finding these two. So when x approaches negative infinity, we converge. We see that our y value converges on this horizontal asymptote, which is 1. When x becomes super large, our graph converges on this horizontal asymptote, which is 1. Right, there, we're done. Now let's look at f. We're going to look at when we don't have a vertical asymptote either for this one, so I want to look at when x approaches negative infinity and when x approaches infinity. And what does our function do? F of x approaches what? So when x becomes super, super small, we converge on our horizontal asymptote of 0. And when x becomes super large, we also converge on that value of 0. So we get 0 over here as well. All right, there's not a lot more problems. In fact, the next couple of problems are a lot easier than what we just did. Now, the number 2, 2a says sketch the graph of y equals e to the power of x minus 6. Well, this is just an exponential, so if we're just going to do a rudimentary sketch, then this graph here is our y equals e to the power of x. Well, what kind of transformation takes place with this -6? It means that the graph is shifted down 1, 2, 3, 4, 5, 6. So we're looking at this is our new asymptote, our horizontal asymptote. And so we converge on that value and then shoot up. So this is our y equals e to the power of x minus 6. All right, so the next one says, hence discuss the value and geometric interpretations of, what does it mean when I have the limit as x approaches negative infinity of this function? Well, that means that I'm going to, what does it mean when I have a massively small x value? Well, for this function, that means I will converge when x approaches negative infinity, then my function of f of x is going to approach, in this case, -6. And when x approaches infinity, then f of x is going to approach something else. It's going to approach, well, when x becomes super large, then our y value explodes to the upside, so we end up with infinity. So we would actually say in this case that when x approaches infinity, that we don't really have that the limit doesn't exist, because there is no limit. Infinity is not a limit. It is, in fact, no limit. So no limit. Now let's look at, well, I basically just did both of these, right? So I also found when x approaches infinity. I've already done that, it's right here. So the answer to this is over here. All right, the last one, this is the last problem. It says, find, if possible, the limit of x as it approaches negative infinity of this function here. So let's look at what this function is here. I've already defined what this graph here is a good sketch of y equals e to the power of x. Now all this 2 does is just make it steeper, so that would mean that my graph is going to, maybe I'll use multiple colors for this. It just means that my graph is going to be steeper, so this would be my y equals 2 times e to the power of x. And then this -3, it just means that my graph is going to move downward, 1, 2, 3. It's going to be shifted down. Let's see if I can, let's use till. So that's going to be this graph here. But what is this negative, if I make my exponent here, the variable exponent, make that negative, well, that means that this is a reflection across the y-axis. So that's going to give me then this other graph that looks like this. And I'm converging, then this is my function of 2e to the power of negative x minus 3. So let's take a look at what it means then if x approaches negative infinity. So x becomes a super small number, so we're going to our x becomes super small, and we can see that the graph is shooting off to infinity. So this limit, so when x approaches negative infinity, then our function in this case is going to approach infinity, which means then that again that there is no limit. There's no limit. Let's look at the last one. So when x approaches infinity, then our function, when we approach infinity, so some massively large x value, we can see that the graph is converging on something. What is it converging on? What is this line right here? Well, since the graph shifted down to -3, that becomes what used to be our horizontal asymptote of y equals 0 has now been shifted down 3 units, so we are now converging on our y value of -3. Hope this video was helpful, and have a wonderful day.